Have you ever, been staring at your phone, just waiting for an app to load, or maybe seeing that little spinning circle on your computer screen? We've all been there, right? Wishing our tech could just work instantly. Well, what if I told you that kind of speed, maybe even 1,000 times faster, isn't just science fiction anymore?
It sounds incredible, doesn't it? But that's exactly the possibility we're jumping into today. There's been this really significant discovery in quantum materials. It could genuinely change the game for electronic speed. We're focusing on a specific material called 1T-2, and scientists have found a completely new method to control how it behaves electronically.
Right. So that's our mission for this deep dive. We want to unpack this research for you. We'll look at what 1T-2 actually is, how this breakthrough method works, and crucially, why it could be so important for future tech. Think faster phones, more powerful computers. It definitely sounds complicated, quantum materials. But we'll break it down, show you how this complex science might offer a neat shortcut to some amazing advances.
Okay, so to really get why this is big news, we need to talk about the material itself. 1T-2. You can think of it as a quantum material. And what's interesting about these materials is how their electrons behave. They aren't just random, they get organized. In 1T-2, they form these specific repeating patterns, almost like ordered ripples running through the material.
Okay, ripples, like organized waves of electrons. What are these called, and why do they matter so much?
Exactly. Waves is a good way to put it. Scientists call them charge density waves, or CDWs for short. Think of them as different ways the electrons can arrange themselves within the material. And these arrangements, these patterns, directly control its electrical properties, whether it lets electricity flow like a metal or stops it like an insulator.
So the pattern changes its whole electrical personality, like flicking a switch.
Precisely. Now, 1T-2 has a sort of default state, especially when it gets really cold. This is called the CCDW state, commensurate charge density wave. In this state, the electrons lock into a very particular pattern. Some papers describe it visually as like a Star of David arrangement, if you could see the atoms. And when it's like this, in the CCDW state, it acts as an insulator. Electricity finds it hard to get through. Not great for fast electronics, right?
Right. You need electricity to flow easily for speed. So that state's not ideal, but there's another state, this hidden one.
Yes, the HCDW, or hidden charge density wave. This is the one everyone's interested in, because in this configuration, the material suddenly becomes metallic. Electricity flows freely, perfect for fast processing.
Ah, okay, so that's the goal. But you called it hidden and mentioned earlier work. What was the catch? Why wasn't this already in our devices?
The catch was stability, or rather, the complete lack of it. Historically, the only way to even glimpse this HCDW state was to hit the material with incredibly fast laser pulses. And even then, it would only exist for minuscule fractions of a second, microseconds, maybe even femtoseconds, just gone in a flash.
A flash, and probably not very practical.
Not practical at all. And to make it worse, this fleeting metallic state only appeared at extremely low temperatures. We're talking below 50 Kelvin. That's around minus 370 Fahrenheit.
Okay, yeah, definitely not suitable for my laptop. So cryogenic temperatures, and you need a high-speed laser just to see it for an instant.
Exactly. You can see why it was considered hidden and, well, pretty impractical for building anything useful.
So how on earth did they manage to make it stick? What was the actual breakthrough?
The breakthrough hinges on a technique called thermal quenching. Now, quenching usually means cooling something rapidly, like a blacksmith plunging hot steel into water. But this is a very controlled, very specific rapid cooling process. The speed has to be just right.
Just right. How so?
Well, the researchers found that if they heated the material up first, above 350 Kelvin, which is actually pretty warm, about 170 Fahrenheit, and then quenched it at a specific rate, they didn't just get the old CCDW state, and they didn't just get a fleeting HCCW state. They stabilized something entirely new. They call it a mixed CDW state.
A mixed state. So not purely insulating, not purely metallic. What does that mean?
It means, quite remarkably, that within the material, you get tiny domains of the insulating CCDW pattern existing right alongside tiny domains of the metallic HCDW pattern. They coexist stably, side by side.
Whoa, okay, so you have both conducting and insulating properties woven together in the same material.
That's the essence of it. And this is the game changer. This mixed state is stable up to 210 Kelvin. Now, okay, that's still cold, about minus 80 Fahrenheit, but it's a huge jump from 50 Kelvin.
Yeah, much, much warmer in relative terms.
Much warmer. And crucially, once you create this mixed state, it doesn't just vanish. It can persist for months. Suddenly, you have a way to harness those desirable metallic properties in a stable, persistent form. It's much more practical.
That really shifts things. But how do they know for sure? How can they actually see these different patterns coexisting? It sounds incredibly small scale.
It is incredibly small scale. They use some pretty sophisticated tools. One is called X-ray high dynamic range reciprocal space mapping, or HDRM. Think of it like an ultra-powerful X-ray that can map out the precise arrangement of those electron waves deep inside the material.
Okay.
And another is scanning tunneling spectroscopy, STS. This one acts more like a tiny probe that scans the surface. It can essentially feel and map the electronic landscape, confirming that, yes, you have these metallic regions right next to insulating regions.
And they mentioned something about opposite chirality, like mirror images. What does that tell them?
Right, that's a fascinating detail. They observed that the coexisting CCDW and HCDW domains were chiral, like left-handed and right-handed versions of themselves, and they were opposites. It helps confirm they really are distinct states coexisting, and it might even give clues about how to better control switching between them in the future. It suggests a kind of structural relationship.
Okay, this is fascinating stuff. Let's bring it back to that initial promise, the 1,000 times faster idea. How does this mixed state get us there?
Right, so current computer chips operate at gigahertz speeds. That's billions of cycles per second. The physics underlying these charge density wave transitions, especially if they can be switched rapidly using light or perhaps voltage in this stable mixed state. It operates on timescales that could allow for terahertz speeds. That's trillions of cycles per second, 1,000 times faster than gigahertz.
1,000 times faster? It's hard to even wrap your head around what that means for computing.
It really is. And it's not just speed. Think about efficiency and size. Right now, chips need distinct materials for conducting paths and insulating barriers. Lots of complex interfaces. But if you have one material, like 1T-TAS2 in this mixed state, that inherently has both conducting and insulating domains, and you can potentially switch between them quickly using light or heat, you could simplify designs enormously.
So fewer complex junctions, potentially smaller components, maybe using less power.
Exactly. You could potentially build devices that are much smaller, more power efficient, and, of course, vastly faster. Faster memory, more powerful processors. It could fundamentally change how we design electronics, perhaps moving beyond the physical limits we're hitting with silicon.
So it's like finding a material that can be its own switch, conductor, and insulator all rolled into one if controlled correctly.
That's a good way to think about it.
Yeah.
It opens up possibilities silicon just can't offer.
Okay, let's dig into the why a bit more. Why does this specific cooling process, this thermal quench, actually work? You mentioned an analogy, like a landscape.
Yes. The researchers often use an energy landscape analogy, drawing from something called Landau-Ginzburg theory. But we can simplify it. Imagine a hilly landscape with valleys. Each valley represents a stable state that material can settle into. If you cool 1T-TAS2 down slowly, it naturally finds the lowest, most stable valley. Think of it as the comfiest spot. That's the insulating CCDW state.
Okay, slow cooling gets you the standard insulator state, the comfy valley.
Right. But the thermal quenching, this rapid cooling, it's like giving the material a carefully aimed push. It doesn't just roll down slowly. You push it over a specific hill on the energy landscape. And this push directs it into a different valley, one that wasn't easily reachable before. This new valley represents that stable, mixed CDW state.
So the speed of the push matters.
Critically, it has to be this intermediate rate, which they measured at around 120 Kelvin per second. It's the sweet spot. Too slow, and just rolls back down to the standard CCDW valley, the insulator state. Too fast, like those earlier laser experiments, and it sort of flies over the new stable valley. It might momentarily reach the HCDW state up high, but it doesn't settle. It just keeps going and doesn't stabilize.
Got it. So it's not just cooling fast, it's cooling at just the right speed to nudge it perfectly into this new, stable, mixed configuration.
Precisely. It's about controlling the path it takes on that energy landscape to land in a useful, previously inaccessible state.
Okay, let's quickly recap then. We've been exploring this amazing quantum material, 1T-TAS2. Scientists figured out that by using a very specific rapid cooling method, thermal quenching, they can create a stable mixed state. This state has both insulating parts and the highly desirable metallic parts, the HCDW, coexisting. And it's stable at much more practical temperatures than ever before, lasting for months.
That's the core of it. And the potential impact is, well, huge. It points towards a fundamental change in electronics, the possibility of terahertz speeds, incredible efficiency gains, and maybe even moving beyond silicon eventually. It really opens the door for using the weird and wonderful properties of quantum materials in actual technology.
So the final thought for you to ponder. What happens when we gain this kind of fine-grained control over the very nature of matter, when we can precisely engineer these fundamental states at will? How might that reshape not just the devices in our pockets, but maybe our entire technological future? It's certainly something to think about.